Good morning, everyone, and thank you for joining us for a quarterly webinar on cyber-informed engineering. Today's conversation is going to introduce cyber-informed engineering as a topic and then perform a deep dive into the CIE principles with illustrations for each one drawn from an engineering case study. The focus of this will be to introduce cyber-informed engineering to an audience and allow them to ask questions. Because of the nature of this presentation and the size of the audience, we would ask that you address your questions to the chat, and during the presentation, we'll try to answer them. The first 30 minutes of our presentation will focus on an introduction to the broad topic of cyber-informed engineering. And if that answers the questions you have, that's intended as a tear-off portion of our presentation. If we've excited your interest and you'd like to stay for the next hour for a deep dive into the principles, that will be the next portion of the agenda. So, going through our slides, I'm Ginger Wright, and I work for the Idaho National Laboratory. I'm Idaho National Laboratory's Program Manager for Cyber-Informed Engineering. I'm joined today by Maurice Martin from the National Renewable Energy Laboratory, and Ben Lampe from the Idaho National Laboratory, and each of us will present separate parts of the presentation. If we can go forward. Oh, sorry, I need to sync to you. All right. So the first part of our conversation will be, what is cyber-informed engineering? To introduce cyber-informed engineering, this is a novel thought about how to enhance cybersecurity protections that is particularly applicable to critical infrastructure or engineered systems. In cyber-informed engineering, we use design decisions and engineering controls, often offered by or conceptualized by the engineers who design the infrastructure, to eliminate or mitigate avenues for cyber-enabled attack. Rather than having a focus on protecting networks and network access, in cyber-informed engineering, we start with looking at the consequences of a cyber attack that could occur on our systems and determining where we could put in place controls that would prevent that impact from occurring. This then means that we can use engineering to eliminate specific harmful consequences that digital technology, if subverted, could cause. Cyber-informed engineering is a practice that is focused on engineers and technicians and will provide a framework for education for engineers and technicians about how they can join into the cyber defense conversation and where they can provide awareness and accountability for cyber defenders for the most consequential impacts of a cyber attack on engineered systems. Cyber-informed engineering builds on the culture of safety already present within many of our engineering disciplines and throughout much of our critical infrastructure. And leveraging some of the same principles for safety, CIE then brings in cybersecurity protections. CIE was documented first in the National Cyber-Informed Engineering Strategy. This was developed by the Department of Energy and released in 2022. In that strategy, in the development of that strategy, the Department of Energy invited a very broad audience, including universities, asset owners, vendors, government entities, and other advisors to think about this concept and to help the Department of Energy design an implementation plan so that they could bring this forward to industry and into adoptions. And in that strategy, those advisors first described what cyber-informed engineering was. They gave some examples of how it could be applied, and they made multiple recommendations for the Department of Energy's implementation. This strategy has been named in multiple administrative cyber documents and is available online. One of the most interesting things that the advisors created were pillars guiding DOE's implementation of cyber-informed engineering. The first pillar they recommended was awareness. that there should be a concerted effort to describe to the population what cyber-informed engineering was and how this differs and offers some advantages when combined with the practice of traditional cybersecurity. And thank you for joining us for this presentation, because you're helping us raise that awareness right now. The second pillar that they recommended DOE focus implementation through is in education. They wanted cyber-informed engineering to be part of engineering education for both universities and technical schools, or wherever engineers may be taught how to leverage digital technology for engineering purposes. And we'll describe later in the presentation some work that has gone on to start that process, but certainly more is needed. They then recommended to the Department of Energy that DOE focus on building the body of knowledge for cyber-informed engineering, including creating some tools that make it easy to apply this idea in specific critical infrastructure applications. Then they said, go and apply it. Apply it to the current infrastructure that exists, what we would call brownfield infrastructure, as well as greenfield infrastructure that is just being put into place. Apply these principles, whether it is legacy or new, and protect what exists. In the final pillar, they also encourage the Department of Energy, because the Department of Energy is often the innovator of first resort and the responder of last resort, to think about research and development proposals and how they could aid researchers to incorporate cybersecurity thinking even into the development of novel technology. The principles for cyber-informed engineering we'll go into in detail in the later part of our presentation. There are 12, and the first principle focuses on consequence-focused design. In this principle, cyber-informed engineering asks the question of what should a system do 100% of the time, always? What are the critical functions that that system must ensure, and the undesired consequences it must prevent? When thinking about consequence-focused design, rather than considering vulnerabilities, system designers think about what would the worst consequences of a cyber attack be. Leveraged with that information, they then start to think about engineered controls and how they could leverage specific controls, whether digital or analog, to prevent the impact, that manifestation of a cyber attack that would be most consequential for a system. The remaining 10 principles focus on the combination of traditional cyber defenses with these engineering approaches. And again, later in our presentation, we'll go into these in detail. So because we mentioned engineering controls, this is a great time in our presentation just to focus in on that idea a little bit and talk about what is an engineering control. All of us have probably stayed in a hotel. And if you stay in a hotel these days, you're issued a credit card-sized key that digitally works with a lock, sends a signal, and allows you to access your room. But anybody with a key that manifests the same signal as yours could potentially open your room. And so because of that digital implementation, you don't have the only control over your room door. However, on the back of your room door, there is often a mechanical device that, if used, could prevent the impact of someone who, whether by fraud or by digital means, got a key to your room and attempted to come in. As long as the bar is pulled across, you've protected your room from their entry. This mechanical device is a great simple example of an engineering control that is employed to prevent the impact of digital subversion of a lock. So one of the things that is certainly prevalent in both engineering and cybersecurity is standards. And cyber-informed engineering very much supports the application of cyber-informed engineering through standards, but will not be a standard on its own. Instead, we encourage practitioners to work through the standards that they already leverage for engineering and for cybersecurity, but keep the cyber-informed engineering principles in mind and be aware that to defend against a cyber attack, you can both protect the network and prevent the impact that the digital saboteur is trying to create. So that cyber-informed engineers had a body of knowledge to draw from, one of the first products that was produced out of the Department of Energy's effort was a CIE implementation guide. In this guide, further descriptions of the 12 principles were created. And for a system development lifecycle, for each of the principles, teams got together to brainstorm what questions could be asked at each of those phases for each of the principles that might guide designers to apply the principles and add cyber-informed engineering principles throughout the concept, requirements, design, development, testing, and implementation phases, and even into operations and retirement. At the very end of the implementation guide, there is a case study that examines a water system upgrade project where the team added cyber-informed engineering to their design process. And the case study describes how that impacted the team's approach to both engineering and cybersecurity and the extra protections that the team put in place. In addition, we've created an open source library that takes all of the publications from Department of Energy laboratories and other Department of Energy sources and puts them in one handy place. This library contains DOE-sponsored research on cyber-informed engineering as far back as 2013, where the first mention of a cyber-informed engineer is made. It contains the work from multiple laboratories and covers multiple application areas, including nuclear energy, the traditional electric system, and even water sector. If you're curious about cyber-informed engineering or have insights for us, we would love to have them. There's a regular community of practice that meets quarterly, and that community of practice guides the research that cyber-informed engineering performs. In addition, there are 3 working groups, one focused on standards, one on education, and one on the implementation of cyber-informed engineering, and they meet monthly. The one that met yesterday had a very highly joined brainstorming session. So this is not all just presentation. The folks that attend are guiding cyber-informed engineering to its next point of maturity, and we would love for you to be among them. In the last year, we've been working on a number of key goals to advance cyber-informed engineering. And in this presentation, we wanted to give you a small update on what we've been doing. So the first goal was to use cyber-informed engineering to improve energy sector resilience. And our hope with that was to have U.S. asset owners and operators leverage cyber-informed engineering principles within their engineering, design, and build efforts. And we have had asset owners adopt cyber-informed engineering, and we've been able to work with them. In addition to achieving that goal directly, we've created a number of supporting deliverables. CIE for clean energy, how to integrate cyber-informed engineering into enterprise risk management, some work on benefits quantification, guidance for C-suite, targeted research and development guidance. So for those who are building the next generation of energy products, there is specific guidance that can be asked even at the product research phase or the technical research phase that might guide the creation of cyber protections. Anything you see in this list that is hyperlinked, you can actually open the hyperlinks even through this presentation, and those documents are available now. We worked on a set of guidance for how to use cyber-informed engineering to defeat some systemic operational technology weaknesses. We created a web-based version of the implementation guide that I showed you a moment ago, and a tool to let CIE be readily applied to microgrids. We also created a number of workbooks, including workbooks focused on substations and advanced distribution management systems. Our second goal was to teach CIE principles at leading U.S. engineering universities. And the outcome we were seeking was to have the curriculum guidance implemented at core engineering, or as part of the core engineering curriculum at 4 U.S. universities with a focus on research-heavy universities. And we've achieved that goal. In addition, this year we will publish the CIE curriculum guide. We're having these CIE quarterly webinars. We have a case study that we're going to walk through in a few moments that focuses on a water booster pump station. And we've made both the slides and a workbook related to that case study public for those who are curious about that or would like to learn more. We're also creating a certification and accreditation plan, a set of curriculum resources that will be made available to any university interested in applying cyber-informed engineering, some laboratory design guidance so that even in lab exercises, these principles could be informed in the research that students do. And we're willing to and actively engaging with universities to integrate curriculum, and as a result of that, we will produce the a CIE adoption report at the end of the year. Our third goal was to incorporate cyber-informed engineering into international digital design standards. And the key outcome we are seeking is to have CIE principles incorporated into at least one international digital design standard. And we've accomplished that objective and also have created a CIE requirements analysis framework, tools for applying cyber-informed engineering at varying criticality levels, cyber-informed engineering validation methods to validate that you are achieving the impact that you had hoped when you put cyber-informed protections into your systems. We'll create a CIE report focused on applying cyber-informed engineering in manufacturing. We have produced a cyber-informed engineering for semiconductors report, and we've identified multiple target standards for alignment with cyber-informed engineering, an implementation plan to achieve that goal, and we are specifically working on cyber-informed integration with the IEC ISA 62443 standard. For our fourth goal, we are conducting CIE outreach and growing our community of practice. We've already talked about that in this presentation. And as an outcome of that, we hope to achieve regular and consistent outreach and robust partnerships with key stakeholder groups to accelerate the implementation of cyber-informed engineering. In this year, we've had 22 conference presentations, panels, or workshops, and we have 290 community of practice members and counting. And our 3 working groups met 32 times over the course of the year. We are also seeking and producing cyber-informed engineering success stories. We also wanted to share our recent cyber-informed engineering publications. And again, anything that's hyperlinked here is available, and you can pick it up and use it right away. These will be available on the cyber-informed engineering websites, and the slides for this will be released. So if you're interested in some of these publications, these slides will lead you right to them. So we've talked a bit about cyber-informed engineering in the theoretical context, and I'd like to take you next through a case study. So if you will, we're now all going to be co-workers for at least the next 15 minutes at a municipal water utility. Our focus will be on the water booster pump stations that are used by that utility. If you've never seen a water booster pump station before, and I bet you've driven by one, this is what they look like on the inside. In a municipal water system, these booster pump stations ensure that the water in the system maintains a consistent pressure so that when subscribers turn a tap or start water flowing, that water flows at the right rate for their application. Maintaining that pressure is a constant dance, especially as seasonal changes and water system changes change the availability of water. Often, pumps are used to maintain this pressure and ensure that water will always flow on demand. There are other applications that can be done in a pump station, including logging information about the water, looking at its quality, and adding chemicals to the water to ensure that it remains safe. But our focus today will be on the pumping itself. And for our water utility, since we're all co-workers, I can share with you that we spend a lot of money and time moving from pump station to pump station, adjusting the pumps and making sure that they're pumping water at the right rate for the seasonal conditions. And we would very much like to turn some of our engineering efforts into additions to our water system and improvements. And we really do see this pump maintenance and water booster pump station maintenance as a burden. And so we applied for and have just received a grant for cloud-based monitoring and control. We're excited about this grant, and we're asking for a number of our staff to come together and consult with us on the best way to install it. And so, since we want to be a responsible system operator, we sent out our teams to gather some information to aid our inspection of this solution. First, we sent our cyber team out, and they went to the control system software vendor and discovered that they have a qualifying secure development lifecycle process. They are very mature. They did a build in front of us and allowed us to see how the software was made and maintained. They provided us a software bill of materials, and when our team investigated the components that were within the software, they found that the component infrastructure was up to date. They also demonstrated a mature vulnerability release process with regular patches and 24/7 support availability if we find a vulnerability or have an issue with the software. We then visited the cloud provider through which the software would be served, and we were equally impressed with their reputability and their qualifications. The cloud provider is both SOC Type 2 and FedRAMP certified, and although we don't need FedRAMP for our solution, it's a great indication of the maturity of this provider. They demonstrated their physical security and how they physically respond to cloud or to events at the internet center that they have. We were very concerned that hosting critical infrastructure services can be very different than other data-based cloud services. Losing data is different than losing water service. And we asked them about their experience hosting critical infrastructure services, and they gave us a number of examples of asset owners who work with them and who depend upon them for other cloud-based infrastructure services. They also demonstrated response and restoration with the solution that we are looking to install and showed us how, if there is an issue with one cloud instance, they could immediately move our solution to another. We also had our IT team go out and look at the installation and determine how well this solution integrates with our tools. What we found was that this tool integrates perfectly with what we have. It can leverage our standard security package at the network entry point. Monitoring and logging traffic on the interface leverages our organizational logging system, so we don't have to specially maintain or look for logs on this system. They'll come in and our SOC can see and respond to any issues. We also found that traffic in and out is encrypted between the cloud provider and our internal network boundary. So we went to an organizational review board and we put the solution forward, And finance and accounting were very excited about how this could save money for our water company. IT and our cybersecurity team were both impressed with the quality of the solution and the solution providers. And though the engineers were excited about the opportunity to use their skills differently, they were a little bit concerned that from an engineering perspective, no one had really thought about how this solution integrated with the water systems needs, and particularly what could happen if a cyber adversary was able to break through all of that security and access the water system. So they asked for permission to do a little bit more thinking and leverage cyber-informed engineering to just take an engineering view of this cloud-based monitoring and control system. So the engineers began to think, what was the worst thing an adversary could do if they gained access to this application? And they realized that an adversary could turn a pump on when it was supposed to be off, or off when it was supposed to be on, or maybe adjust some of the settings. They examined that idea more closely and recognized that the settings that this digital system would access had been governed with some physical aspects of the pump. So even though an adversary might be able to change the pressure setting on the pump itself would not operate at a place that was dangerous, even if it was told to. So that was a good thing. If an adversary turned a pump on or off at the wrong time, they analyzed and realized that within 2 hours they could respond to that. They could take the pumping station off of autonomous control and operate it manually for at least 2 weeks with the staff that they ordinarily had. And after talking with the cybersecurity team and the IT team, 2 weeks seemed to be reasonable. But as they thought a little bit further and they thought about what is truly the worst thing that could happen, any adversary that could turn a pump on or off could turn it on and off and on and off and on and off and on and off, and might do so so quickly that they either broke the pump or created a water hammer effect with the potential of damaging the water booster pump station. This, they realized, would likely drive an 18-month outage to order a new pump, to repair any damage in the water system, and it would require rerouting how the pressure system worked to keep that station open. Especially if an adversary could perform this action at more than one water booster pump station, that would be cataclysmic. So this is a place, they thought, where even with the great security that they acknowledged the tool had, it might be useful for engineering to bring in just a little something extra that would limit the impact that a cyber attacker had, even if they broke through all of that wonderful cybersecurity. So in this case, they recognized that a mechanical time delay relay would be a great solution. With that relay, every time period, it opens, accepts a command, performs it, and then closes again until the time period is exhausted. So say every 30 minutes, the pump could receive a command and execute it. And while that would keep the engineers from being able to issue finely grained commands to the pump unless they did it in the water booster pump station out of line with that mechanical time delay relay, it would also prevent the adversary from being able to operate the pump any more quickly than the mechanical time delay relay would allow. With this design, the team went back to the organizational review board and reported. They reported that with the time delay relay option, it would add $20 plus a necessary outage for each water booster pump station to the cost of implementing the cloud solution. Finance and accounting was still fine with that, and engineering and operations felt comfortable that they had a solution such that even if an adversary broke through the cybersecurity, there was still something to protect the water systems. So that is a race through the high-level topic of cyber-informed engineering and our cyber-informed engineering program. The next part of this presentation will go into a deep dive of cyber-informed engineering principles, and I hope that you choose to stay with us. I'd like to invite Maurice Martin and Ben Lampe to come on camera. Take it away, gentlemen, and thank you.
Well, good morning, everyone. And thank you, Ginger, for that presentation. Here we see this 12 principles again. And as we go through these in the context of the water pump example, one thing that I ask you to keep in mind is kind of the idea that is a driver for a lot of CIE work, which is that any digital system can be compromised given sufficient time and resources. And if you keep that in the back of your mind, a lot of these CIE principles will come into focus very well. And what I liked about the water pump example as presented by Ginger was notice how the whole conversation about the water pump changed when that question was raised by the engineering operations team. And that triggered an understanding of we need to think through what are the most critical consequences that might arrive. So let's go to the next slide, please. Oh, and I should say the way we discuss presenting this is I'll queue up a general discussion of each of the principles, and Ben will take over applying that to the water pump example. So the first principle, and the one that kind of underlies all the other principles, is consequence-focused design. As Ginger said, this is where you think about your functions. Which critical functions must happen correctly? What does the system have to do? And then the undesirable consequences that must not happen. That would be catastrophic if they occurred. And these are foundational ideas and foundational questions to ask during this process. And consequence-focused design actually changes across time and system maturity. So it's worth asking this question again and again as your project or your system evolves and changes over time. And next slide, and Ben.
Yeah, absolutely. So if we think about consequence-focused design in light of the pump station, when you think about the pump station and you ask what's its reason for existence, you can see how maintaining pressure, maintaining a certain amount of pressure really becomes its critical function. The reason it exists in the system, because as you might imagine, pumping water over long distances, either up elevation or just long distances, requires these buffers to help, you could say, re-energize the system. And so if we take that function in mind, you can start to trace it to very key components that help, you could say, focus your attention on where a more evaluation from your engineers may be worth it in light of all the components in your system. So the nice thing about this is it helps you to focus on the critical components that help contribute to that critical function. And the premise of asking those questions of what's worst that could happen, how we should respond, that really helps filter out really to figuring out what's the worst case consequence, the one that's necessitates that additional control mechanisms beyond just your cyber, but in addition to your engineering controls. But you can start to see how this principle really helps, you'd say, pull back the layers within the system to really drive to a specific component. In this case, as Ginger is alluding to, showed the pump really is that core component amongst all the components that naturally draws our attention for future additional evaluation through other principles. So I'll hand it back over to Maurice to jump into the next one.
And the next one is engineering controls. illustration on this slide showing the hierarchy, which ones are most effective. And this kind of is something that's so intuitive that maybe we miss it, is that the most effective controls are those that are physical in nature. Ginger gave the example of the door latch on the hotel room. It's the final barrier that is going to be most effective. And maybe not so obvious in considering this hierarchy of controls is that when you are planning a system and you want to secure it, thinking about in terms of engineering controls, what are the physical things that we can build into the system that will prevent the worst consequences? This enables you to move security forward in the life cycle. In other words, get it in there earlier, all the way to the conceptual and design phases. And this solves a problem we see in operational systems. We build it and then we tend to apply security after the fact. And even in research settings where it's sometimes the idea is like, well, let's build a prototype, then red team it. Well, the problem with that is by that time it's quite possibly too late to make major changes to the system. By bringing in security earlier, you can build it in, and that enables you, in some cases, to reduce the cyber footprint, the digital footprint for protection that you need later. In other words, if you've already engineered out the most impactful consequences, then you can right-size your digital security controls and perhaps save money and effort by not overbuilding those. Ben?
Yeah, absolutely. So when I think about this from the perspective of the engineer, this resonates a lot with our safety culture, because our safety culture takes those worst case type thinking already into practice. And there's really an opportunity for that kind of dual credit application. And when we think about the pump station, there's operational modes that we're designing to that have timing characteristics, set point characteristics, logic characteristics. And really it's the opportunity to really center in those and ask the questions, could I complement these or replace them or protect them with other mechanisms to reinforce some timing, reinforce a set point, reinforce some logical characteristics that I've programmed into the operation of this. And as you saw on the pump station, by focusing on that pump and asking those questions around the logic that's used to maintain that pump, we can recognize an opportunity, in this case, for a time delay relay, that any command sent to us, we can hold it in for a set period of time. And that time enforcement mechanism is not cyber susceptible, like the logic that might be in the PLC is cyber susceptible. So you're taking advantage of multiple dimensions to help protect really that critical function that's being expressed here in this pump station, and knowing that control helps be deterministic, governed by the physics of the materials in that relay and mechanisms like that. But you can see how really the opportunity there's a lot of opportunities to be behold in a certain process system like this pump station, but it's really up to you to decide which one you might want to realize a actual design around. So I'll hand it back over to you, Maurice.
Thank you. There we go. The secure information architecture. Now, your system is going to have information architecture. There will be pathways for control signals. There will be data flow. There will be telemetry. How this is designed can be improved upon and informed by bringing the engineers into the conversation. And when they are able to answer like, well, these are the critical functions and these are the possible consequences, that helps the IT folks to understand, oh, this data stream is most critical. If manipulated, And if a data stream is manipulated and that data is accepted by the system, are there protections against the consequences? And also what drives decisions about how much protection to put on those data streams. So the engineering input becomes critical to the information design. Ben?
Yeah, and when I think about this principle, this is one of the good principles that help us connect the two groups, the two units in an organization, the cyber staff and the engineering staff, because it's really the engineer that has that understanding of what data is involved in the system, right? There may be thousands of data points that are being controlled or managed or processed within a control system, and a cyber staff may not have that understanding about the characteristics, the plant dynamics. They just may see that data stream, and so they are left to say, okay, I'll try to catch it all. I'll try to manage it all with varying levels of success. But it's really that engineer who understands the specific data values, the specific data points, especially around this pump. Like, what's the start command? What's the stop command? What's the expected values, the set points, those type of things. And amongst that diversity of data, it's the engineer that understands which specific data might have the greatest impact, the greatest relationship to, hey, if I affected this set point as opposed to those set points, there's much clearer, you could say, relationship to a worst case scenario in that context. So it's the engineer that can provide that clarity to a cyber staff who's managing the monitoring solution so that they can target their protections, their monitoring, their layers to help say, given this set point, I want all of it. Or for these other set points, we can be aware of them, but there's a different behavior around those data values. But it's that conversation that the engineers are best positioned to help describe the value and where any manipulation amongst all the data has the greatest impacts, so that cyber can help align to that story versus just trying to do it all. So hand it back over to you, Maurice.
Thank you. Next principle is design simplification, and you see the illustration there. Reading from left to right, is you can think of that as an early iteration of a design, and then more mature design on the right, where at each iteration the device under consideration gets simpler. We've all heard that complexity is the enemy of security. It can result in intentional or unintentional use, and it can result in emergent behavior, which we don't really want emergent behavior in our OT systems. We want them to be do what we want them to do. So in thinking about high consequence, low value complexity within digital function, it's natural to ask, well, what can we do without? How can we make the system simpler? And this speaks to our relationship with our vendors. Can we go to them and say, I want something with less features? Vendors may not like that because features are how they differentiate their product and how they get extra margin on their sales. But we can still ask the question, can these features be left off to the system or removed? Can they be turned off in a way that they will no longer be available? Ideally, they would be removed entirely, because even features that are not always accessible to authorized system users may still be accessible to adversaries. And there's some nice smart grid examples of that out in the literature. But design simplification, of course, always requires trade-offs. If there will be certain things that you can't use your device or your system for, if you embrace design simplification. So if you have to weigh the simplification against the incremental value of extra features and other things. And if features are removed, you need to go through some process to verify that they have in fact been removed. Ben?
Yeah, you brought up some good points, Maurice, about trade-offs, because this one, there's some market influence here. And so when we think about the pump station, right, there's a couple opportunities that arose from an engineering point of view, both from the PLC side of it as well as the drive mechanism for the pump. You might ask the question, okay, in this pump station, is it a pump station that needs to be able to vary the pressure? And if that's a requirement, right, that necessitates a elevated, like a variable frequency drive type dynamic on your pump to be able to continuously adjust the rate at which the pump is pumping. But if engineering recognizes the opportunity where this pump station really just needs to maintain a static type pressure and doesn't require adjustment, and the pump's been sized in such a way that given this speed, you will produce this pressure. Those opportunities reduce identifying mechanisms where you might not need the complexity of a variable frequency drive. You could just go back to a simple on-off control and reduce that threat space, knowing that your system and its expected behavior fits more in line with that design simplification practice. And in this case, this pump station didn't need the network connected VFD drive receiving the messages from the PLC to perform its behavior. It could solve the critical function through just a relay driven pump and on-off type behavior. Another example in this type of system is with a PLC. When you go buy a PLC, you're often buying the PLC and it has the ability to communicate with Modbus, with Ethernet IP, with maybe a REST API, maybe a suite of different protocols are available to communicate and interface with that PLC. But as engineers, we could say we're designing it to communicate with Modbus and Modbus only. So the question is, what can I do to remove those other protocols? And you may sit there and say, well, I can't, because I can't go and adjust that firmware, what have you. So I have to disable them, but it's a software disable. So if a adversary were able to get into that development and adjust that runtime to allow Ethernet to be communicated in and adjust values, now that's a off-channel communication. If you can't remove it, this is where you could bring in the previous protocol, secure information architecture, as a countermeasure to say, monitor for those other protocols to see if they start to be used. Where I couldn't simplify, that could inform how I can monitor for abuse of a protocol that I don't expect to be used based on the design. But you can see how engineering can drive that conversation in the event you're not able to simplify due to trade-offs or market constraints in your products, or in your system design as a way to achieve this protocol, or this principle, excuse me. So I'll hand it back over to you, Maurice, for the next principle.
Next principle is layered defense, and this is a illustration that I really like, the so-called Swiss cheese model. And the idea is that the attack is beginning on the left and trying to thread its way through all of these different defenses to the right. And as you see in this case, it stops with the second to last defense. And this is again very applicable to cyber-informed engineering. If you think about these engineering controls that are meant to address the most critical consequences, they're not going to address all the consequences. The water pump example is not going to. Well, let me use the hotel room example. The latch on the door is not going to protect your room while you are out of the room. You have to be in the room in order to activate the latch. So you need some other defense for your valuables that you might leave in the room when you're out and about. And usually often there's a safe included in hotel rooms, which provides a nice defense. So that's an example of that kind of layered defense. But generally, engineering controls will not prevent things like data exfiltration, and so you have to look at your system and think about those risks as well, and what value you place on preventing data exfiltration and what that would mean to your system. But certainly you want those analog mitigations in the layer defense example in order to address those worst impacts. And as well as think about prioritizing your consequences so that you are certain that your priority consequences are going to be mitigated. Ben?
Yeah, absolutely. So especially when we introduce engineering controls as an additional layer in this layering of defenses, and we start to relate that to the consequence focused nature that we got out of the first principle there, and we start to ask the question, how many layers is good enough, or how many layers do I need to become to move the risk into an acceptable region, and so what CIE offers in this, and as we relate to the pump house example, when we introduce the time delay relay with the security and the monitoring we apply to the network and the PLC and the tunneling to the cloud provider that is able to issue commands to the pump, you start to track all those layers that contribute to the overall protection, in this case of the pump and its ability to maintain pressure, but from a consequence side, its ability to prevent the overcycling of the pump, whether for thermal damage or for water hammer effects in the larger system. You can see the use of engineering controls provides a strong independentness, for lack of a better word, between those layers, which I think is a powerful characteristic in this principle as you identify both cyber layers as well as those engineering layers now, as well as safety layers, those that provides that rich conversation in this example of how the organizations work together to come to a very strong cybersecurity risk strategy or cybersecurity protection strategy for this worst case consequence that they deemed unacceptable for operating their system. So I'll hand it back over to you, Maurice.
Active defense is the next principle, and this begins when you put yourself in the shoes of the attacker and begin to think, well, if I wanted to create some of the worst consequences, what would my kill chain look like? What would be the steps that I would execute to achieve this particular consequences? And again, we're bringing in the understanding that we get from the engineers to help us identify first what those consequences might be and what how they might be achieved, and then design the defenses. So I think that it's thinking about the defenses with the in light of principle one, the consequence focused design. Ben?
Yeah. Something that this principle really puts the onus on is your operators, your technicians, those ones that are maintaining and stewarding the day-to-day operation of the system, and that staff and the engineering staff, having them recognize or understand what are those precursor events. Is there a certain relationship amongst the data, or if you're watching the pressure right, is there a certain precursor that could help start to have that reaction by your operators, by your technicians, to invoke some incident response or to invoke some even upfront actions to participate in the defense in that very active relationship. And it's largely why it's active defense. And so you really make sure you have that conversation up front, because when you're figuring that stuff out, you don't want to be figuring that out as an event is occurring. You want to have that understanding of what are those precursor events, what are expectations with our vendors, our supply chain. Do we need additional contracts to help in that response, or that response to those precursor events, to help promote our active defense with the use of the operators, the technicians, the engineers that are responding to this? Because there is operators in this relationship managing from that cloud solution to their pump stations that are connected. And so making sure that they're trained to that is really a common practice in our operational world. But this adds that other layer of, are we also training to cyber adversarial actions and those worst case consequences that we want to recognize and make sure we participate in, and not making those realized in our day-to-day operations of the system. So Maurice, I'll hand it over to you.
Interdependency evaluation. This is applying the same idea that we discussed earlier, that any device or system can be compromised if assuming sufficient time and resources. We've been applying that to our internally, but we also need to think externally, and what can happen if some of the other organizations, entities, systems that we are connected with become compromised. What is the possible chain of consequences? And we have to look at a lot of different types of interdependencies: physical, cyber, logical, and geographic. Are we connected organizationally or operationally to these other systems? And with a particular emphasis of looking at any kind of cascading effects that might occur and what those would do. So again, this is a situation where that understanding of critical functions and the actions that must be avoided, that principle one comes into play, and we have to look at all of the possible failure scenarios of that would be in play here. Ben?
Yeah, and when we think through this principle, especially in this context, there's really two levels to this, and it's both within the system, right? There's a complexity there of different components working together and contributing to the delivery of the system, especially when we recognize that there's also water treatment here and things like that. So there's the interdependency there. It's hard to water treat when there's no pressure because there's maybe no moving water. So there's that type of interdependency, but there's also a much larger interdependency in this relationship where, okay, there's support for this system, whether there's power being delivered, right? There's the interdependency relationship of, if I lose power to the site, that also represents a interdependency that may be worth analyzing or protecting, or might inform how you design the system, especially if you want the system to ride through a power outage. But this principle helps draw that out. And specifically, as we're introducing cloud solutions, there's a new interdependency that wasn't there before. Are we setting up the dynamic where the system can only run with the use of the cloud? Or do we have the resilience in our system design that says, in the event the cloud goes out or we lose the network, we also have the ability to run it manually or run it locally, or it's able to run in more of an automated fashion during those periods of time? Those are the type of things that get drawn out by performing that interdependency evaluation, especially in light of what we've agreed upon as the worst case consequence, and stressing what are the external utilities that are also used in that situation. So, Maurice, I'll hand it back over to you.
Okay. Digital asset awareness. The phrase sounds like it'll be related to asset management, and it is certainly. But we're going to stir a little bit of failure mode analysis in there as well. We need to look at our devices and question our own assumptions about, or examine our assumptions about how they work and what their failure mode looks like, and then propagate those downstream through our system. Are we accounting for all the possible failure modes? Again, thinking in terms of any digital device can be compromised given enough time and resources. Assume that compromise, propagate that downstream, the physical effects, and then see if we are seeing some of those high consequence events. And that kind of drives what we want to know about our devices, and including they're all the way down to the firmware, the physical characteristics of the device. So it's traditional asset management with a little more engineering focus as well.
Yeah. So this principle, a lot like the first one, really helps set the environment, understand the environment as you're getting kind of that cyber-informed engineering perspective at hold. And so in this conversation about the plant, the booster pump station, there was a decision to say, okay, let's get the pump operations in the cloud solution first. But the next natural conversation is, okay, we also have this water treatment, the chlorinator system that currently is offline, or say not connected to the cloud solution, but it's a natural conversation of saying, okay, our next phase of the project is we want to also connect in the chlorinator, and that requires some new components, network connected components, those type of updates or upgrades to the system. But you can imagine as an engineer, when you start to select a component, digital asset awareness asks the simple question, what are the digital features here? How many digital features? What's the extent of those digital features? What are they able to do? What's the bounds, right? Is there a range of values that can be supplied? How are those values used? So you can start to see how this principle really helps understand the influence that digital operations has within the component itself, but also within the larger system that component is contributing to or enabling. And so you can ask questions of, is it, especially in light of the chlorinator, how is the chlorine dispensed? Is it dispensed with hardwired? Is it adjustable? How is it adjustable? Oh, it's adjustable via digital means through the cloud solution would be the goal. And you can use that understanding to then bring into engineered controls, secure information architecture, layered defenses. You could start to see how this principle really helps provide some foundational understanding for the other principles to then operate on, just like how consequence-focused design helps set some of the foundational understanding by which to focus the other principles against. One of the key questions, and especially in the chlorinator, especially if you are thinking about operating that remotely, how would you know the product's actually dispensed? Because an adversary can position themselves in the middle and present a false story to your operator. So is there a technique then you can work in the system to help ensure that it's actually dispensed and the actual amount is proper? You didn't overfill the chlorinator into the water like we saw with some attacks with like the Oldsmar water treatment, where they tried to overfill the lye in the system. So you can see how that relationship can be really explored through digital asset awareness by probing what's the extent of the digital influence that's being brought into the system. And that's ever growing in this modern age, because if it's not digitized today, it's being digitized tomorrow. and more smart meters and smart sensors, smart actuators, smart components are finding their way all the way down to the field level devices. And so this question really helps test those waters in preparation for a lot of the other principles. So Maurice, I'll hand it over to you.
Cyber secure supply chain controls. And this is really about getting your vendors on board with the idea of CIE, asking them to include engineering-based protections in their devices. Your effort to implement CIE is going to be a lot easier if your vendors have already done that for their devices. Otherwise, you have to go in and kind of do your own reverse engineering and thinking about how different devices might go off the rails. If they're unable to do that, at least they should be able to share with you information about their security postures and some of their design decisions. In terms of your own, internal process during the design, be sure to document your assumptions about the security of the products that you're incorporating. I think a lot of us do this, and then maybe don't put those assumptions under a microscope. I think doing so can be very informative and can also give you a spot to work from if you are going to go back and verify those assumptions. You may find that they are not what you thought, and at that point you can have a discussion with your vendor to see if you can move them more in that direction. And don't be shy about using your contract enforcing mechanisms to drive that conversation. And again, this sounds like a lot, but you are focusing on the most impactful consequences. So if you do that, it's maybe less overwhelming.
So, right, cybersecurity has a lot of good governance in this space about supply chain risk, and what we are seeking to amplify with cybersecure supply chain controls from a CIE context is really the engineer's relationship in this discussion, where the engineer knowing what the critical component is, or knowing what I'll just leave it at that, the critical component of the system, so in this case the pump, they can convey that understanding to their vendor, so the vendor can also participate in that security. This is especially important when we think about contracting as part of maybe incident response or just defense in depth, allowing your vendors or so in this case, right, the example that comes to mind is, okay, if you lost this pump station, a response action could, hey, I need to roll a truck that provides kind of temporary pumping at that location to maintain pressure. And if your organization, in this case, didn't have the capability of rolling a truck that had a onboard temporary pumping, and you may be contracting that to an organization, allowing them to understand the importance of when you call them and making that part of the expectation and developing that trust helps ensure that they're also kind of working with you with the same worldview, especially from that engineering context. But this enhancement to supply chain governance and supply chain in the larger cybersecurity is allowing the engineers to help further inform the focus or the level of attention or the service level that would be expected when responding, especially to a worst case consequence, and the components that are involved in that, because those components are often supplied through a supply chain. And so it allows them from that point of view, as well as what Maurice was putting on or kind of centering in, is allowing the supply chain to participate in the security. You can imagine if a time delay component was part of the pump inherently, whether it's used or not would be the system designer's responsibility. But having that feature in there is a cyber-informed feature that could be used by those that need it, as an example. I mean, so this principle helps drive that principle out, and especially in the context of the cloud provider relationship in this project, since the cloud provider is now part of that critical function of maintaining pressure. Do they have that awareness? Have they, because they're going to be probably patching the systems in their cloud infrastructure. What's that relationship look like? How is that system patched? And is that relationship worked out between this water organization and the cloud provider? Can the asset owner reject or accept a patch? Do they have the ability to have that influence in that relationship? Those type of things become important characteristics in working through that supply chain, especially in this cloud dynamic where they're giving responsibility over to the cloud to run the environment that server, that technology is running in, that then calls back or provides commands, provides connectivity back to their infrastructure. So you can see how this supply chain control principle helps kind of make sure that relationship's understood and defined. And I think that helps support kind of the larger supply chain governance that's core to cybersecurity nowadays in this modern age. So Maurice, I'll hand it over to you.
And resilience is the next principle, and this asks the question: what happens when a failure occurs? In this case, a cyber attack that is successful, and can I engineer in features that will allow me to hold on to some level of system operation, even if it's in a reduced or degraded state? And this is, you can think of this as failing better, or sometimes called graceful degradation. Kind of the classic example of this is an escalator, moving staircase. Its most common mode is that it just freezes up, in which case it becomes a staircase. It's still perfectly usable, but it's just not giving you that boost up the incline. So the engineering piece of this is, first of all, understanding how physical components might be used to keep the work going, even if it's not as efficient or as profitable as it would be otherwise, but is still able to be somewhat useful even in its diminished operating mode. Ben?
Yeah, of all the questions, this is my favorite personally. When I ask how do I turn what ifs into even ifs? And in this example, right, there's obvious questions that we ask around that. What if the attacker turned all the pumps on or off? Especially if we think about the attack going beyond just a single substation, or sorry, not substation, beyond a single pump, booster pump station. And just like in active defense, having those precursor activities, events understood up front, this one really speaks to at what point have we entered a mode of operation that's unacceptable? It's been so far degraded that it's into a new environment, a failure type environment. But engineers can help understand what's an acceptable level of degradation that, while it's not optimal, it's still effectual in its ability to deliver the capabilities of the system. Right? What's that range of pressure that is still acceptable to meet other requirements in the system? But engineers are the ones that can help best answer those questions in the context of this idea of planned resilience. What if the application vendor, the cloud vendor, reported an adversarial attack? They got ransomware, for instance. What if their application just stopped working? Having these type of questions really helps inform some alterations in the design. There's a really good exercise that we've put out in some of our material called A Day Without Automation. Have you explored that in a tabletop type exercise? Because that might inform how you might design the manual operational components of the system, because it may not be enough to just have manual operations. You want to have the manual operations in such a way that you don't need 5 people there to maintain the manual operations, because you might not have the staff to maintain 5 people at a certain location. So those are very key aspects to this. And as you see on the screen, when we think about responses to those questions, we start to see how plan resilience helps inform that fallback strategy in the event of component failure from an adversarial action, or what is acceptable. But once again, just like active defense, knowing this upfront is key, because this is not things you want to help solve in the event as it's occurring. Because one, that'll become very inefficient, or two, that's not how incident response was meant to be played out. Is you want to figure that stuff up front, and plan resilience allows the engineer to help contribute to that conversation in a very important way. So Maurice, I'll hand it over to you.
Thank you, Ben. Engineering information control. Basically, make sure that the engineering aspects of your system design are protected, as well as other aspects. If the attackers know less about how your system operates, it will be harder for them to attack and produce those very high consequence events. Think about how information about your system might leak through design documents, both digital and printed. Presentations. I've seen some kind of shocking examples of organizations sharing their inner workings in presentations and presenting information that would be very useful to attackers. What might be said on social media are, and you know, think about your employees and what they're saying on their own social media, including things like LinkedIn, where they are wanting to show off their technical skills. Are they showing off too much? And design partners. Make sure your design partners are treating your information as securely as you are, in order to make sure that it's not accessible for those with bad intention. The engineering angle on this is that figure out how the information could be misused if it were made available, and how to make sure that that information is contained.
So when I think about this organization, one of the challenges that a municipal water has is naturally a lot of their material has to be released through public record. It's part of kind of the bidding process, or even when you think about city council and divulging things to the public, because it's a public service, and the relationship with tax and those type of things. You can see how this has a challenge, just like supply chain. There's constraints here that sometimes are outside your control, but working with the engineers to ensure that while certain information must be released, what truly needs to be released, right? Knowing that a pump exists, do we have to get all the way down to divulging the make and model, or is it sufficient to just release this type? And you can see how this has a strong relationship with a lot of our data governance that we do in cybersecurity. But allowing engineers to inform within their suite of information that they're managing, what's the behaviors that we should operate with as an organization, both in the public facing side, even within the organization, just like we do with a lot of, you could say, common IT information with network diagrams, but that conversation is pulled down into, okay, P&ID diagrams, the control function diagrams, and those type of things. That is best addressed by how the engineer thinks about that information security, where others might not be able to address it in the same way. But a lot of that information may have to be released, but you would want to think through that in a very similar way to the data governance and data protection practices we do in the larger IT picture. Maurice brought up a good point. When we think about those that are operating the system, what does their social media look like, or even the resumes for those, or not the resumes, sorry, the job postings, what type of information are you divulging, and does that contribute to open source intelligence that an adversary can then use to, when they're trying to plan an attack, they can target the technologies, target the type of software development kits that you may be using, which and then to that last point there on the screen, allowing the engineers to recommend what the kind of specifics, those could be obfuscated to really balance that trade-off of, we have to divulge a system due to public records, but there's certain characteristics that that are truly necessary for the public record type thing. And it's a tough conversation, but I think it's one that engineering can contribute strongly to the organizational cybersecurity practices. So Maurice, I'll hand it over to you for our last principle.
Last principle is organizational culture, and this is getting everybody on board with all of the 12 principles presented here today. Get this C-suite read into this and understanding about their role in terms of supporting this effort. The assessment of risk has to be both cross-functional and cross-disciplinary. You need to get your IT folks and your engineers talking to each other, getting them to sit down. And if changing the organizational culture seems like a big lift, and just remember, Ginger mentioned the safety culture that is now in place in industry. We have made so many improvements in safety. That is such a big success story. We've done this, and we can do it again with cybersecurity. It just requires everyone to understand their role and have regular discussions and keep looking for pathways to improvement. Ben?
Yeah, absolutely. So you saw that at the kind of tail end of the introduction to this pump station, where as the organizations were approaching this new solution for good reasons, right? There's intention that's going to be able to make our organization more efficient in how we manage our suite of booster pump stations. But as we walked through each organization and got their buy-in to this, both from a financial, from a technology, from a cybersecurity point of view, allowing the engineers to now have that cyber-informed behavior, allow them to participate in the conversation and further enhance cybersecurity within the organization. I think it's been said, right? Cybersecurity, just like safety, is an all hands on deck type situation where the behaviors of your certain roles and responsibility in the organization all contribute to a very effective and mature cybersecurity program, where it's not just one part of one organization, but each person with the organization has a different role to play. And while a lot of the conversation is driven out of the IT organization or the cybersecurity organization, tapping into what engineers can now provide, really as far back to the conception requirements phase, really represents how organizational culture further enhances and allows everyone to perform their role aligned with those security goals of the organization, that risk acceptance line that we're all trying to achieve as an organization. And engineers are positioned for addressing it at the depth that they design the systems to, just like they do with safety and a lot of the other constraints that they have to balance when designing and maintaining a system, especially in this modern age. But the fact that engineering could drive that implementation really helps show how this is further enhanced by involving engineering through a cyber-informed mindset. So with that, Maurice, I'll hand it over to you.
Thank you, Ben. Next slide, please. And those are our 12 CI principles. I would say that we can go to the next slide and review the CIE publications as well. If you are looking, Ginger mentioned the CIE library that we have online. It's very comprehensive, can be a little overwhelming. So you may want to start with the publication shown here on slide 59 and think in terms of getting started, doing a little reading. One of the really good resources is the implementation guide, the first one under publications. A lot of the others kind of build on that. So I would recommend that to be a good starting point. And that brings us very close back to the top of the hour. Ginger mentioned our community of practice and our working groups. Very much welcome your participation in those, and we can provide information about how to connect to those and attend to those. Then I lead the standards working group, which looks at how to align or how to make standards development organizations aware of CIE and eventually incorporate it into their standards. And we meet monthly. We'll next meet on the first Wednesday of November. But we have the other working groups, and we have the overall community of practice. And I will say that the discussions are lively and interesting and wide-ranging. So anything to add to that, Ben?
I fully support that notion that they are lively and energetic. So, but if we fundamentally appreciate what all the you'd say expertise that people bring to that, because the people are coming from all the sectors, and so we're able to tap into that expertise to really find that common thread through engineering and seeing how that cyber-informed characteristic can further enhance the practice of engineering.
I don't know if Ginger, did you have any closing thoughts, or should we?
Just to say thank you. Thank you for joining us today to learn about cyber-informed engineering. We would be delighted to share more information with you. And there's an email in the chat, cie@inl.gov. If you missed our presentation, if you don't receive the slides as you had expected, or you'd like more information or a chance to join our working groups, please correspond with us there. We would love to talk with you further.